I just want to know what whole problem, the some problems we have discussed in terms of people. Is it okay if I haven't did anything for me? Oh yeah, yeah, that's okay. Yeah. Mhm.
All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Good, good. All right, so plan for today, we're just going to continue with our lecture notes on beam equations. Okay. So we have we're going to finish up the exam. I think we almost finished an example on Tuesdays. We'll finish that up, and then we'll go over the topic of distributed loading and see how that works out. Okay. I don't know if this is going to take the whole time today. So if we do end it a little bit early, we may start the next thing, which is frame equations, or we may just end early. We'll see. Okay. All right. So some announcements, and so remember, homework 1 is due tonight, and so make sure you guys get that in. I do have the next homework ready for you guys, and so that's going to be posted early tomorrow morning. But and so it's going to be based on the beam equation stuff, and then the frame equation stuff that we're going to do. We're going to do next. Okay. All right. Are there any questions I can answer before we get started for today? Yeah.
By any chance, will we have more time on this homework?
On homework 1?
Yeah.
I can give you until Sunday night. Does that work?
Yeah.
Okay. All right. I'll give you guys until Sunday night for this homework. Okay. I'll wait until Monday to post the next one. Okay. All right. So we'll I'll give you guys until Sunday night to finish up this homework. Okay. Yeah, it's a bit long, especially the 2D stuff. So okay. All right. Any other questions I can answer? Okay. All right. So let's go ahead and get started. Let me scroll up here a little bit. So I think we left off right in the middle of the example last time. Okay. So the example we were doing last time was we were doing this direct stiffness problem. So we had 2 beam elements, A and B, in a spring, and we were interested in computing the deformations. In this case, the deformation would be for nodes 2 and 3. Okay. So we went through their element stiffness matrices, and then we're now at this part here of the assembly. Okay. Okay. So this is the first time that we've combined beam elements with other types of elements here. So we're combining beams and springs in this case. Okay. We've done beams, we've done springs and truss elements before, but those are pretty much the same. Okay. But when we combined spring and beam elements, there were a couple kind of subtle wrinkles that we kind of went over last time. So kind of the first thing that we noticed was that beams, their deformation modes are different than springs, right? So beams are capable of transverse deformation as well as rotation, whereas springs are only capable of expansion and contraction, which are axial deformations. Okay. And so if you look at the geometry for this problem here, I put the spring perpendicular to the beam, and I did that very deliberately so that I combined both things. When the spring does its axial deformation, it's actually in the same direction as the beam's transverse deformation. Okay? So what that allowed us to do was to basically treat our spring here as a one-dimensional element instead of going through the whole two-dimensional 4x4 system. Okay. Yeah.
What if the load was placed somewhere else along the beam? Would the effect still be the same?
It would.
Still perpendicular?
Yes. Yes. So in this case, so if the load were placed here on node 2, the element stiffness matrices would all still be the same. Now, if the force were in this direction, so let's say that we're doing an axial force here, we'd have to change our approach a little bit because the beam it can't handle any axial deformation now. And so in that case, we'd either change this to maybe like a truss element, or maybe we change it to a frame element. So a frame element is actually capable of both axial transverse deformation and rotations all at once. So yeah, it depends on the nature of the loading. So you want to make sure your loading is actually consistent with the deformation that's out. Mm-hmm. Yeah. All right. So now that we have this 1D element for the spring, we can go ahead and go to assembly here. Okay. So that was kind of the last thing that we left off. And so in particular, when you're combining beams together with springs and trusses, you have to be aware that we often like to put this EI over L cubed factor out in front. Okay. Now, if you're just doing a problem, if you're just doing a problem with beams, this is no issue, and so you can just kind of fill the space here without any problems. But if you'll notice the spring here, the spring element stiffness matrix is only comprised of the spring constant K, okay? And so, when we incorporate this into the element stiffness matrix, we want to make sure that everywhere we put the spring, that it does equal just K in that slot, okay? And so if you notice what I did here was that I added K, but then I multiplied K by the inverse of this factor out in front, okay? So I have a K L cubed divided by EI. And so when you multiply this factor through to here, right, it actually cancels out that factor, and you end up with K. Okay, so you just want to make sure that you're consistent with the units here. And this kind of gets mostly dicey when you're combining different types of elements. Okay? And we'll see this again in the next unit with frames as well, right? But that's kind of just a small thing. I kind of want to make sure that you guys caught. Okay. So now that we've assembled all the elements here, it's now time to apply the boundary conditions. Okay. Okay. All right, and so our boundary conditions in this case we have two fixed supports or fixed constraints. Okay. These are occurring at nodes 4 and node 1. I don't know why I did in that order. It should be 1 and 4. But what this basically means is that for any degree of freedom that's associated with node 1, so that's d1y and theta 1, okay, we're going to apply our Dirichlet boundary conditions on these rows here. So we're going to change everything to 0 except for the diagonal, okay? It's going to be 1, 0, 0, 0, 0, 0, 0, and then 0, 1, 0, 0, 0, 0, 0. Okay. And of course, in the forcing vector, we're going to transform those into zeros as well. 0, 0, 0. Okay. And then we're going to apply the same on node 4. But remember, node 4 was only connected to the spring, and so we only have d4y. And so that means that only this last row here, this d4y row, is going to get transformed to zeros. Okay, so we have 0, 0, 0, 0, 0, 0, 0, 0, 1. Okay. All right. So while the iPad's catching up, or while the internet's catching up, let's look at our loads. And so our loads in this case, we just only have the one load, and so that is a downward load applied on node 3. Okay. I believe it's node 3. Let me control that. Let's see. Yeah, we have a 50 kilonewton load being applied on node 3. Okay. So that means we're just going to change F3Y into 50 kilonewtons. That's 50 minus 50,000. Okay. And of course, everything else that's in the forcing vector that is not that we don't have a load for, we're just going to apply 0 for that. Okay. So that means F2Y, M2, and M3. All of these are going to be 0. And of course, all the empty space in the global stiffness system is going to be 0 as well. 0, 0. Okay. All right, so now our system here is ready to invert, and so we can plug these matrices and vectors into MATLAB and solve for their result. Okay. And so the solution from MATLAB is the following. So we have d1y, theta 1. Both of these are 0 because of the fixed constraint. Okay, tertiary boundary condition. Okay. Then we have d2y and theta 2. So d2y is minus 0.02 meters. And theta 2 is minus 0.012. So the units technically the rotations are unitless, but not really. So the units that we typically use are the ones that's computed from here are radians. So they're not degrees. You can convert those radians to degrees if you want, but leaving it in radians is just fine. All right, so then we have d3y and theta 3. So d3y is a minus 0.0638 meters, and theta 3 is a minus 0.016 radian. Okay. And then finally, we have d4y. d4y is just 0 meters. So that's the fixed constraint. Okay. So that's the solution for this Yeah. Any questions? Yes.
You scroll.
Yes. Mhm. Mhm. Any other questions on this example here? All right, so the last thing I want to do with this example, before we move on to distributed loading, is compute the reaction forces. So if you remember from the lecture Tuesday, what we talked about was that once you have your deformation solutions, you have your values for d and thetas, you can actually plug that back in and solve for the reaction forces at the constraints. Okay, so we have two constraints here. So we have a constraint on node 1 and a constraint on node 4. And so we know that in order to keep the structure in static equilibrium, there has to be forces applied at these constraints in order to balance out all the forces in the system. Okay, so let's talk about how to compute that, or let's actually do it in this case. Okay. So to compute the reaction forces at nodes 1 and 4, where the constraints are, we need to multiply our deformation solution So that's the solution that I have boxed just right above this. We need to multiply that by our global stiffness system, the one that we had before applying the boundary conditions. Remember, this is right after the assembly step, before the boundary condition step. And so, if you're not like me and you're smart and didn't erase the one we had before, this would be easy. But since I was kind of an idiot and I forgot that we had this part, so we have to write it again. So let me go ahead and write our global stiffness system again. So EI over L cubed multiplied by 12, 6L minus 12, 6L, 0, 0, 0, 6L, 4L squared, 6L, 2L squared, 0, 0, 0. Of course, all of these have numbers, but I'm just doing it symbolically just so that you can see. All right, so you can see here I'm writing in the entries for the first element stiffness matrix, and we're just getting to the second one now. Zero, 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 zero. So minus 12, minus 6L. Then we have 12 plus KL cubed over EI minus 6 and minus KL cubed over EI. Those are the spring constant terms, okay? If you already had this in your notes before, you know, I'm just writing it down just for completeness because I erased the other one that was for the boundary conditions. Okay, but that's our 7x7 global stiffness system. So that's what we obtained after assembling the element stiffness matrices for our 3 elements. Okay. And we're going to multiply this by our deformation solution. So we have D1y, theta 1, D2y, theta 2, D3y, theta 3, D4. Okay. And since we're doing this after we found the solutions for these, we can just plug these right in. So I'm going to go ahead and pull the solutions down from here. Okay. So D1y is 0 meters. Theta 1 is 0 radians. D2y is minus 0.02 meters. Theta 2 here is minus 0.012 radians. Okay. D3y is a minus 0.0638 meters. Theta 3 here is a minus 0.016 radians. And the D4y is 0 meters. Okay. All right, so we have a 7x7 square matrix multiplied by a 7x1 column vector. Of course, you know, this is most easily done in a computer. You can do this by hand. It's just going to take forever. And so if you have this matrix already in MATLAB, you can just do the matrix vector multiplication. Okay. And then if you do that, you're going to get another vector solution here. Okay. Which are going to be all the reaction forces. So this is F1y, M1, F2y, M2, F3y, M3, F4y. All right, so we kind of do this a little bit backwards than what we usually do. So in this case, we already have the deformation solution and we're solving for the forces instead. Okay. All right. And so if you do this multiplication, okay, you get the following solutions. So F1y is equal to 37.23 kilonewtons. Okay. M1 is equal to minus 893.62 kilonewtons meters. Okay. F2y is 0, M2 is 0 Newton meters. Okay. F3y, this is actually our original load, and so this is actually going to give us minus 50 kilonewtons. Okay. That one's not a reaction force. That's actually the external force being applied onto the model. Okay. M3 is equal to 0. And then F4y is equal to 12.77 kilonewtons. Okay. All right, so it looks intimidating. There's a lot of values and a lot of variables kind of floating around here, but it's just, you know, you take your deformation solution, which if you're doing this in MATLAB, you already have a variable for it anyway. Then you just take your element stiffness matrix and then you just multiply it, and then you just view the result. Okay. So after we cover frame elements, so we'll probably spend all of next week covering frame elements. Then the week after that, we'll probably just we're going to discuss the MATLAB implementation of these methods. Okay. And so you'll see that, you know, by this point, usually people are getting pretty sick of these problems. I'm sure you guys are kind of getting sick of them too. After next week, you're going to be really sick of these problems because frame elements, like I'll be honest, frame elements suck, but they are a necessary part of learning this entire thing. And so at that point, you're going to be really ready to learn about the MATLAB programming, because the MATLAB makes these a lot easier than what we're doing here. Okay. All right. Any questions on this? Yeah.
So just the forces at nodes 1 and 4 are just balancing out the force on node 3.
Exactly. Yep. Question?
So if you have, so how do you find what is the maximum force needed before the whole system fails? Is
Yeah.
that where you solve that?
Yeah, no, good. That's a good question. So to do that, you would need to compute the stress in these elements. And so remember what we talked about back in trusses, there's a way to compute stress by taking the deformation solution and multiplying it by its Young's modulus and things like that. What you would need to test to see if any of those stresses exceed the yield strength of these materials. So that's typically how it's done in these cases. That's going to be a lot easier to do in ANSYS. And then once we do ANSYS, I think a couple weeks from now, we'll discuss that there because it's ANSYS computes these stresses automatically. Right, any other questions on this example here? Okay. All right. So then the last topic I want to go over with beams is this topic of distributed loading. Okay. So a distributed load is a load that's distributed over typically an area, but we can just be more general and say a load that's distributed over a region of space. Okay. And so visually, you know, they usually look something like this. And so if we have a beam, right, a distributed load would look something like, you know, we have a load that's distributed over your entire beam, just like that. Okay. Okay. So typically, you know, that's how we think of loading a lot of times, because you know what we have been doing up to this point in our direct stiffness problems is we've been applying our loads at a point. Okay. So if we have a beam, even if we break up this beam into, you know, let's say we break them up into 3 elements, A, B, and C, right? All the loads that we've been considering have been applied at the joints in between the elements, right? Nothing distributed over the whole thing. Okay? But the reason we've been doing point loads is that this is something that just meshes very naturally with the direct stiffness method, right? Because think about how we apply our boundary conditions in our global stiffness system, right? When we have a point load or a load that's applied at a point, we just insert that value directly into the matrix, okay? So, you know, you can make the argument, and in fact, this is actually quite true, that in order to apply a load in a finite element sense, they need to be applied at these, we call them at the nodes, okay? All right. But we want to incorporate distributed loading, because distributed loading is a lot of times how we think of things, right? And so let's say that this beam is supporting a structure or building above it, right? And so that weight of whatever that structure above it is being distributed across the entire beam. Okay. And so we have a little bit of a conundrum where, you know, distributed loading is often kind of how we naturally think of these types of loads in a lot of situations. Okay. But we can't directly apply the distributed loading in a finite element context, okay? And so what we need to do is we need to be able to convert a distributed load to point loads so that we can use that in a finite element context. So basically we want to form something like this. Okay? Let's say that we have, I'm just using beams as an example here, just because beams are kind of the most natural way to think about these, okay? And so let's say that we have a beam with a distributed load up top. So what I have here is just an even distributed load, okay? And what we want to do is we want to transform this into a situation where we have, you know, just loads applied at the ends, okay? So we have F1y, F2y, and maybe we'll put some moments in there as well. So we'll say M1, M2, okay? Okay. So that's our goal here, okay? And we want to do this in a way where, you know, if we were to simulate this with finite elements, the effect of the deformations on the right should be equivalent to the effects on the left, okay? So we want to, you know, we don't want to just choose these F1y, F2y, you know, kind of haphazardly. We want to do it in a smart way so that we still capture the amount of deformation, the amount of stress, the amount of deflection as accurately as we can, okay? Okay, so to do this, we're going to make use of a physical principle called work equivalence. Okay. And all that basically states is that, you know, the amount of work that the distributed loading on the left is performing should be equivalent to the amount of work that the nodal loading is applying on the structure itself, okay? Because in both cases, when you apply a load on a structure, it's going to deform, right? It's going to generate stresses inside the material, you know, it may fail, okay? And so no matter if you're going to apply the load in a distributed way or in a nodal way, the amount of work done, the amount of deformation done should be equivalent. Okay. So mathematically, it looks like this. And so, you know, to compute work, work is nothing more than just a force multiplied by a distance, right? And so if we take our W of X, okay, so our W of X right here, this is our distributed load function. Okay. So usually it has in our case, it has units of force per length. Force per length. Okay. Those are its units. Okay. And if we multiply that by the resulting deformation, I'll call this dy of x. Okay. Both of those are functions of x because they're going to vary, you know, as we go along the beam. Okay. And then if we integrate this, so integral of w of x dy of x dx, okay, that's the work done by the distributed load. So this whole quantity together is the work. Okay. That has to be equivalent to the same work done by the nodal load, by the concentrated loads. Okay. And the work done by the concentrated loads is actually easier to compute because we're also going to be solving for their nodal deformations as well. Okay. So for example, so for a two node system like this, we have F1y, F2y. Okay. So if we take F1y and we multiply that by the nodal deformation there, okay, so we have F1y multiplied by D1y. Okay. And then we add that to F2y and D2y. Okay. So again, we have a force multiplied by distance. Then we have the work done by those nodal forces. Okay. And then we also have the work done by by the moments as well. So we have M1 theta 1, M2 theta 2. Okay. So these four terms right here are as the work. So everything on the right there is the work done by the concentrated loads. Okay. Okay. And so we're gonna make use of this function of this relationship here. So let me box this. It's going to be kind of key to our whole operation here. Okay. So we're going to make use of this relationship and the fact that these two quantities have to be equal to solve our issue, to solve our conundrum. Okay. All right. Any questions on this so far? Okay. So the reason I'm bringing this up, you know, before we kind of go further, because the math gets a little bit hairy from here. The reason I'm bringing this up is that this is something that has to be done internally in finite element softwares as well, right? And so you'll see that so we have a couple ANSYS activities planned that oftentimes when we run ANSYS or we run any other finite element software, you know, we typically apply our loads in a distributed sense. Okay. This. Okay. So whether it be like you know, like the weight of an object applying a force, or maybe it's like wind pressure, like we're simulating we're simulating a building that's exposed to wind pressure, or like a freeway sign. Okay. Typically, we naturally just distribute loads over a space. Okay. But even for finite element softwares, you know, a distributed load can't be used directly with a finite element context. And so internally, what's happening is that ANSYS or Abacus or whatever finite element software that you're using is that they're transforming your distributed load into these concentrated loads so that it can actually form the linear system. Okay, the linear system is kind of key to the whole operation for everything. Okay. Okay. All right. And so the way we're going to use this expression here is, you know, we're going to work primarily on the left-hand side of the equation. Okay. Right. So we're gonna be performing integrals, and then we're gonna obtain, and we're gonna match it up with the terms on the right. Okay. Because the things that are on the right are the things that we want, right? And so if we look at f1y, f2y, m1, m2, okay, these are what we want. And so the objective here is how to get the left-hand side to match up with the right-hand side. Okay. Okay. So if you look at the left-hand side of this equation, there are two functions that we need to plug in for. So the first being w of x. Okay. So I will just right off the bat say that w of x is usually given to you. Okay. Because that w of x represents your loading that's being applied onto your structure. Okay, so that's something you intrinsically have knowledge of because typically you are the engineer, you are the person that's applying this load. Okay. And so you know we'll do an example with the given w of x. That's essentially just given to us. Okay. The biggest question mark here is this dy of x function. So let's work on that. And so if we plug in a certain type of expression for dy of x, then we can actually evaluate this integral and obtain what we need to. Okay. Okay, so that dy of x is the spatial deformation, a spatial variation of deformation in the beam. Okay. Okay. All right, so we need to plug something in here. More importantly, we need to plug something in here that relates what we have on the left-hand side of that expression to the right. Okay. So what we're going to plug in, we're going to plug in an expression that it actually incorporates the nodal degrees of freedom. So I'm not going to go into the specifics of how this expression here is derived, just because it's we're a little bit short on time. But if you're curious, you know, it also involves, you know, Euler-Bernoulli beam theory. So I don't want to get too much into it because on Tuesday I kind of skipped that derivation of the element stiffness matrix for the beam. This kind of relates back to that. Okay? And so I'll just say that this is from Euler-Bernoulli beam theory. Okay, so I'll just kind of give you the ending expression. So, okay, so the ending expression here is we have 2 divided by L cubed d1y minus d2y plus 1 over L squared theta 1 plus theta 2 x cubed, okay, plus bracket minus 3 over L squared d1y minus d2y, okay, minus 1 over L 2 theta 1 plus theta 2 x squared plus theta 1 x plus d 1 y. So it's probably a little bit bigger and a little bit more complicated than you probably originally thought. But what's key about this expression here is that you can see we have the nodal degrees of freedom. So we have d1y, d2y, theta 1, theta 2. Okay. All right. So what we can do from here is we can plug this in, and so we can take this expression, plug it in here, okay, along with a given load function, w of x, and we can evaluate that integral and solve for the distributed load, okay? All right, any questions on this before we do an example? Okay, all right, so let's do an example. Okay, so let's consider a beam, and this beam is going to be subjected to a linear ramp loading. And so it's a loading that's going to ramp up as we go from one end of the beam to the other. Here's our beam, and our loading is going to look something like this. All right, so the function that we're given for w of x is 5,000 times x. Okay, so it's a linear function, so it varies with x. Okay. All right, so there's no finite elements here, so we don't have any boundary conditions or anything. Okay, so all we want to do in this problem is we want to convert this distributed loading to concentrated nodes or concentrated loads at the endpoints. All right, so we're gonna make use of our work equivalence formula. We're gonna make use of our deformation formula, or excuse me, deformation equation, and then our w of x. We're gonna evaluate the integral, and then we're going to equate terms. Okay. So what's gonna follow is probably at least 20 minutes of just math. So I hope you guys are ready. Okay, so let's go ahead and get started. So to fix this issue here, to solve this problem, we're going to make use of work equivalence. Okay. And so our work equivalence formula is that we need the length of the beam. Sorry. So the length of the beam L is 1 meter. Okay, so our work equivalence formula, we have the integral from 0 to L of w of x times dy of x dx is equal to f1y d1y plus m1 theta 1 plus f2y d2y plus m2 theta 2. Okay. So we're going to plug into this expression here. And so we're going to plug into the left-hand side and evaluate that integral. right, so the right-hand side, we're just gonna leave it alone. And you'll see where the right-hand side comes in, but we have plenty to do on the left-hand side. Okay, we have integral from 0 to L. Let's plug in for W of X first, and so W of X was given to us in the problem. This is 5,000 X, okay? Then we're going to plug in for dy of x here. So for dy of x, we're just going to plug this monstrosity in there kind of as it is. Okay. All right. So you have 2 over L cubed d1y minus d2y plus 1 over L squared theta 1 plus theta 2 x cubed plus minus 3 over L squared d1y minus d2y minus 1 over L 2 theta 1 plus theta 2. Okay. That's multiplied by x squared plus theta 1 x plus d1 y. And all that is integrated by x. Okay. So that expression there, the dy, looks very scary, but know that most of these are constants. Okay. And so remember, we're integrating this in x. And so the only terms that we actually have to integrate are the x terms. And so there's only 4 of them. So we have an x cubed, we have an x squared, we have an x, and we have a constant term. Okay? And then x is going to be multiplied through all this too. So you're going to see that a lot of these terms are just kind of they're just kind of freeloaders. So they're just going to be kind of along for the ride the whole time. All right. Any questions on this? All right. Okay. But before we move on here, let's plug in because there's a lot we can actually plug in for, and let's kind of simplify this a little bit. Okay. Okay. So in this step here, I'm just going to be simplifying a lot of things. I'm gonna do a few steps at once, but let me summarize each of the steps that I'm going to do. Okay. So number 1. Okay. First thing I'm going to do here is I notice that I have a 5,000. Okay, that's just a constant term, and that's something that's multiplied by the whole thing. And so if you remember from calculus, the constants don't really affect the integration. And so what we can do is we can pull the 5,000 out in front. Right, so we can pull that 5,000 out in front, and we can kind of just forget about it until the end. Okay. All right, the next thing I'm going to do also involves that first expression there, that 5,000x. I know that this x here is multiplied by everything that's within these square brackets. Okay. So what I'm going to do is I'm going to distribute this x all throughout. Okay. And if you'll notice, all it's going to do is that it's going to raise the power of x for each of these by 1. Okay. So instead of this first term being x cubed, it's going to be x to the 4th. This term on the end here, instead of being x squared, it's going to be x cubed. This theta 1x is going to become theta 1x squared. And then this d1y, which is a constant term, will become d1y squared. Okay. All right, and then number 3. So steps 1 and 2, you almost always want to do those for any of these types of problems. Step number 3, sometimes it helps if your length is something convenient. In our case, our length is very convenient. It's just 1. So everywhere we see L, we're just going to plug in 1 for that. Okay. Okay. So after we do that, we should have a form that's much easier to integrate. So let's go ahead and apply all these steps here. Okay, so we have a 5,000 out in front. Our integral now is between 0 and 1 because we plug in from L for L. Okay. And then from here, we have 2. That 2 was over L cubed before, so but we're going to plug in 1, so it's going to just be 2. That's 2 d1y minus d2y plus 1 over L squared, so that L squared is just going to just become 1. Okay. So this is plus theta 1 plus theta 2. And all that is multiplied by x to the 4th, okay, because we distributed that x throughout. Plus minus 3 d1y minus d2y minus 2 theta 1 plus theta 2. Okay. Once again, plugging in for L there. We multiply that entire term by x, and so its power of x raises by 1. It goes from x squared to x cubed. Okay. Then we have theta 1x multiplied by x, so that's going to give us a theta 1x squared. And then our last term, d1y, which is just a constant term, we multiply by x, that becomes d1y. And we're integrating over dx. Okay. All right, so now that we have our expression in this form right here, we're now ready to integrate. Okay. And the integration is actually a lot easier than you think, because a lot of these terms are not going to be integrated. They're essentially just constants, right? So everything that we have here, okay, everything in here, and all of these guys, okay, everything that I've circled in purple, these are not functions of x, and so we don't need to integrate, okay? The only things we need to integrate are just the x terms, right? And so we have integral of x to the 4th, that's pretty easy. That's x to the 5th divided by 5. And integral of x cubed, so that's x to the 4th divided by 4. And then x squared and x the same thing. Okay. So our next step is to integrate. Okay, so we have our 5,000 here. So, even though we pulled the 5,000 out, a lot of times it's easy to forget about them. So make sure you bring them along every step of the way. All right, and then from here we have 2 d1y minus d2y plus theta 1 plus theta 2. We integrate x to the 4th. We integrate x to the 4th. We get x to the 5th divided by 5. Okay, plus minus 3 d1y minus d2y minus 2 theta 1 plus theta 2. Okay. We integrate x cubed. We integrate x cubed. We get x to the 4th divided by 4. Then we have plus theta 1 x squared. We integrate x squared, and what we get is x cubed divided by 3 plus d1y. Integral of x is just x squared over 2. And then we're going to evaluate this between 0 and 1. That's the integration, and so it ended up just being integrations of polynomial terms, so not too bad. Okay. The next step is going to be to apply the bounds of this integration. So for every term that we have x in there, we're going to plug in 1 and we're going to plug in 0 and subtract. Okay. So next step is evaluate. Next step is to evaluate the integration. Okay, so I'm going to do this kind of term by term, just to make things a little bit easier. Okay. All right, so let's not forget the 5,000. Okay, don't forget him. We have 2 d1y minus d2y plus theta 1 plus theta 2. Okay. We have an x to the 5th over 5, and so that's going to be, we evaluate this at the bounds, we get 1 to the 5th divided by 5 minus 0 to the 5th divided by 5. Okay. Okay. Then we have a plus minus 3 times d1y minus d2y minus 2 theta 1 plus theta 2. Then we're going to evaluate x to the 4th over 4. And so that's going to be 1 to the 4th divided by 4 minus 0 to the 4th divided by 4. Okay. Okay, and then we have our final two terms. These ones are much shorter. We have theta 1 times 1 cubed divided by 3 minus 0 cubed divided by 3. Okay. And we have d1y times 1 squared divided by 2 minus 0 squared by 2. All right. Let me pause here just to give people a chance to pick up on the writing. Are there any questions on anything we've done here so far? All right, lots of integration. We're in the home stretch. We're getting close. Okay. All right. So of course, everything with 0 here is just going to cancel out. So I'm just going to just, everything with 0, I'm just going to put an X through it. Okay. And so the next step is we're going to distribute. Or in other words, this is going to be another step of simplify. Because now that we perform the integration, we have a lot of common terms. And so first step is to distribute all the fractional terms or fractional coefficients. Okay. And so we have a 1/5 that's going to distribute through all 4 terms on the first one. We have a 1/4 distribute there, 1/3, 1/2. Okay. Let's do that first. Just because it's quite a bit to do. Okay. We have 5,000 multiplied by 2/5 d1y minus 2/5 d2y plus 1/5 theta 1 plus 1/5 theta 2. Okay. So everything there was from the first expression. Okay, so I just took that 1/5 and distributed all throughout. Next, we have a plus minus 3/4 d1y plus 3/4 d2y minus 1/2. So that's 2 over 4, so that's 1/2 theta 1 minus 1/4 theta 2. These last two are easy, so we just have a 1/3 theta 1 plus 1/2 d1y. now that we've distributed all the fractions, it's a little bit easier to kind of keep track of everything. So let's do another simplify step. And here we're going to combine all the like terms. So if you notice that, we have a bunch of D1Ys, D2Ys, theta 1s, theta 2s, okay? And they show up multiple times. And so let's go ahead and combine all of them, okay? All right, we're going to use the 5,000 in a second, so don't worry about it, okay? Okay, so for D1Y, we have three terms here. So we have the 2/5, we have the -3/4, and we have a 1/2 here, okay? And so I can't do fractional math in my head right now, so we're just going to look at the answer. And so this is going to add up to a 3/20 D1Y, okay? Okay, next we have D2Y. So D2Y, we have a -2/5 and a +3/4 here, okay? So we combine those together and what we get is a positive 7/20. Okay. All right, next we have the theta 1 term. So for theta 1, we have a positive 1/5, we have a -1/2, and a positive 1/3. Okay. You add those all together, and what you get is a positive 1/30. Okay. All right, and then finally we have theta 2. So we have a positive 1/5 and a -1/4. Okay. So 1/5 -1/4, that is a -1/20. Right. So finally, now that we're at this point, we can distribute the 5,000. Okay. And so we distribute that 5,000, we get 750 D1Y plus 500/3 D2Y plus, or excuse me, plus 1750 D2Y. We have 500/3 theta 1 minus 125, or excuse me, 250 theta 2. Okay. All right. So that was a lot of math. Okay. All right, but we're just about done here because now that we've evaluated this integral, now we can apply our work equivalence here. And so remember when we started this whole this whole integration here, what we said was that this expression here is equivalent to the work done by the concentrated loads. Okay, so this is going to be an F1y D1y plus F2y D2y plus M1 theta 1 plus M2 theta 2. Okay. And so if we just match terms up, right? And so we can see here that the 750 D1y, the only thing that could be equal to is the F1y D1y. Okay. So we have the 750 F1y. Okay. Both of those are multiplied by D1y, so that tells us that F1y here is equal to 750 newtons. Okay. Next, we have the 1750 and the F2y. So that tells us that F2y is equal to 1750 newtons. Okay. All right, now next we have M1. So M1 must be equal to 500 over 3 Newton meters. Okay. And then finally, we have this minus 250 multiplied by theta 2. The only term that could be is M2. That's multiplied by theta 2. Okay. If M2 is equal to minus 250 Newton meters. All right. So what we've done here is we've taken our distributed loading, a loading that ramps linearly and distributes kind of smoothly, and we found out their equivalent nodal loads in this case. Okay. So now if this were a real finite element problem, now we can actually start the finite element problem. So now we can actually go write the element stiffness matrix and the assembly and the boundary conditions. And so, you know, all this that we did is only half of a typical problem. And so you would then plug this, you would then start the real direct stiffness problem from here. But, you know, I'm not going to do that to you guys. You know, this was enough for today.
So
All right.
basically, this is just a setup for the problem.
It's a setup. Yeah. Yeah. It's a problem in itself. You have to do the pre-problem, the problem before the problem. All right. Any questions on this? Okay. All right, so that's it for beams. So we have about 8 minutes left in class. So I don't want to start the next thing yet. I'm going to do a little bit of a change of plans, and so I think, you know, just kind of judging where we are. We've been doing this nonstop linear algebra and math, and so I think I'm gonna move the ANSYS stuff up a little bit. So Tuesday we're gonna do our ANSYS activity. I know I promised you guys that kind of as early as the first week, and so I think it's about time. I think this is a good break point too. You know, before we start getting into frame stuff. So Tuesday we'll do our first ANSYS activity. We'll finally get to open the software. So if you're joining at home, you know, make sure that you've installed the software on your computer. I think I sent out an email on that early in the semester. If you're here in class, you don't have to worry about it. These computers in the room here have ANSYS on them. So Tuesday we'll do ANSYS, and then we'll go from there. All right, so thank you guys for coming today. I don't have any more our plan today, so we'll just go ahead and end a bit early. So hope you guys have a good rest of your day. Hope you guys have a good long weekend. Remember, Monday is President's Day. So I know we don't meet on Mondays, but if you have class on Mondays, well, you don't anymore. So that's a good thing. And I will see you guys on Tuesday for ANSYS. Question. So do you need to submit screenshots of MATLAB for the homework? You do not. So just give me the final solution. Yeah.
I had a question. So, I think there are notes that
Yeah, so that was a typo. So if you look at the notes here, I added one of these terms wrong because there should be a negative 1/4 by changing the plot. Oh, yeah. So there's that should be a negative. So you can do positive 1/5 minus 1/4. Instead of 9/20 here, that becomes a -1.
Oh, okay. Yes. And so does it look like this?
Exactly. Yes.
So it's negative, so you're normally this way, so that's why it's down this way.
Yeah, so actually, that's a good point. So for this one, the distributed mode, we use the positive sign, but the arrows we point down are negative. So if you want it to be kind of consistent with like y-axis being this way, it should be a -5. That would actually flip all of them.
Oh, all right. The minus. So then they would be this way.
Yes.
Okay. Okay. I understand. Thank you.
What level of accuracy do you expect for the solutions? Because I was off by like, I guess that's 4 decimal points.
Oh, that's
So that's fine?
Yeah.
Okay.
I'm mostly looking at the first, most of the first non-zero.
Okay,
Yes.
and also, what was it? Just, I think you have.
Oh, yes,
yes.
yes, I
Yeah.
got that. I read that right before I ran out the office, so yeah, this,
So.
yeah, note
It's
three.
like 1, 2,
Yeah.
4, 1, 3, 4.
1, 3, 4.
Okay, just making sure.
Yeah.
And also,
I think that's-
so I got an internship for summer, I'm gonna be driving to Georgia during finals week. Is it possible to take the finals like the week before?
So we don't have a final exam in this.
Oh,
It's gonna be a
it's like
final
one
project.
project, and is that gonna be like presented or something during the last week?
It's just a final report. The due date, the submission date for the final report is gonna be May 1, whatever that Monday after final.
Okay.
So yeah, it's no problem.
All right, sounds good. Thank you so much for.
Yep.
It's probably bad how long it's been since I've eaten like. I got my best.
Oh, yeah.
Like, what I did is, I choose this week, yeah, I considered, this week as a positive direction, and this thing is a negative. I just want to know, we have to take the lowest node, or do we, by number, or by the
By number,
orientation?
by number,
Basically, I have to take this thing.
yes.
Okay.
But you can choose the higher one too, just be consistent with it. So I say the lower node just because I think that's an easier way to be
Easier.
consistent. But if you want to choose the higher node for this one, you're gonna get the same answer. It's just that, as long as you pick this node as the center point for all of them, then you're gonna end up with the same one. So just be consistent.
So what I did is, I took this node for calculating this matrices.
Yeah.
What I did for angles, so for this one, I took angle is like 180 minus 60.
Sure,
I
yep.
like this. So for this thing is 180 minus 45.
Yep.
So for this thing, I should take 0, or it's like 180,
You should do 180 for now.
because I took 180 and I don't know, I messed up somewhere and I didn't, my answers are not matching.
Okay.
Rest of the same steps are the same, right?
Yes.
How we just do, it's just the angle, we have to take cos sign and we just
Yes.
have to put.
Yes. Send me your work, so I can scan it and then.
Kind of messy.
That's okay,
I
that's
just-
fine.
I think
no,
I
you're-
have messed up somewhere here because I'm getting too big values. I
Okay.
don't know.
It should, if the values are too big, that shouldn't be because of the angle. There might be something else, but yeah, usually, but yeah, go ahead and scan it to me. I'll take a look. Probably tomorrow because I'm pretty hungry. So, but yeah, I'll take a look at these.
And this due
Sunday.
on Sunday, right? You want to talk this? You want to
I was asking the same question, so I basically did -60, -45, and 0.
Okay, yeah. Yeah, as long as you're consistent with like where the origin is for each of them, whether it be the higher numbered node or the lower numbered node, and then which way the positive axis is. As long as you're consistent with all that for all of them, you'll get the same thing. Your sign might be a little bit reversed, but the magnitude.
Thank you.
Yep. Mhm.